Alright, 1 second.
Hello, everyone. I'm just testing the microphone. Testing 1, 2, 3. Can you guys hear me at the back? Yes. Okay, that's fast. You guys can hear me too? Yes, good. What about if I speak from here? You can't hear me, Stefano? Yeah? Cool.
Awesome. Did you want to hand your mic to Kanishka to kick things off? Technology. We're kind of live streaming as well on our YouTube channel. That's kept us all sort of slightly connected during COVID-19 over the past 12 months. We were actually going to do a data engineering meetup just before sort of COVID really hit us, and here at Rokt. And so it's really great to be back here at Rokt. Really thank Kanishka and the team here for hosting us tonight. You know, it's been an interesting 12 months. Haven't seen this many people in an office space for quite some time. But, you know, yeah, so, I mean, if you haven't met me, my name's Peter. I'm, you know, organised the Sydney Data Engineering Meetup, and, you know, it's been really good fun in the last 4 years sort of building it out. Leo, one of the organisers from DataEng Bytes, is going to take us through sort of our data engineering conference that we're running at the end of August. But before we dive into that, we've got Kanishka is going to tell us a little bit about Rokt. It's always great to hear about some awesome companies doing really interesting stuff with data engineering. So thanks, Kanishka. A round of applause. Thank you.
Hey, everyone. Welcome to the Data Engineering Meetup at Rokt. My name is Kanishka. I am the VP of Engineering at Rokt. And if you don't know much about Rokt, I'll give you a brief rundown. We are a marketing technology company. We work with big brands, e-commerce brands like Ticketmaster, Hotels.com, Expedia, HelloFresh, to name a few. But what does that mean for engineering? It means that we have to deal with a lot of traffic, a lot of data, and we are a very data-focused and ML-focused company. We have about 200 odd employees, and out of those, we have about 140 in R&D, based in Sydney. We're always looking for great engineers, and especially data engineers. So if you want to find out a little bit more about Rokt, you can obviously have a chat with me. Some of our friendly staff here wearing the Rokt t-shirts and the hoodies. You can have a chat with them, or you can scan the QR codes here and register interest, and you will find out a little bit more about Rokt. Also, hopefully everyone has had some food. If not, I don't know if there's anything left, but there was some pies there and drinks over here. And hopefully everyone's gone through the scanning, and you've scanned the Server New South Wales QR code. And last but not least, we have the bathrooms, the female bathrooms on the right side, and then my right side, and then the male bathrooms on the left side. I'll pass it on now to Leo, and you'll hear more about Rokt a little bit later from Ivan. Thank you.
Okay. Thanks, Rokt. Yeah, really appreciate being in person again tonight. It's definitely new and exciting after a year in the dungeon. So I just want to give a quick rundown. We're doing an exciting conference, both virtual and in person, given it's going to be safe and COVID restriction free. So it's called Data Engineering Bytes, and it's a conference centered around real-world data engineering problems and solutions. So hopefully everyone's attending the right meetup and you're all interested. And we're kind of aligning to 4 different themes. So one of them is data at rest. which would be, I don't know, scaling, data warehouses, data storage, all that jazz. Data in motion, so event-driven architecture, data pipelines, IoT, and of course, streaming. Data for machine learning. So we're interested in getting models into production, your machine learning pipelines, your feature stores, all that, and data you can trust. So you're probably sitting there at this point saying, I don't know, where can I sign up? Where can I get tickets? You got to kind of hold your horses. They're not out yet, but they'll be out in the coming weeks. What we're looking for at this point is submitting more talks. So I'm personally quite interested in those kind of real-world, nitty-gritty data engineering problems, and we want to hear your problems and your solutions. So the call for papers is still open. It shuts on the 2nd of July, I believe, to confirm. But we're still looking for submitting talks, and we also have mentorship programs available if you're quite new to speaking or it's your first time. I do want to give a quick shout out to all of our sponsors as well, because without them, these kind of events can't happen. So we have Snowflake, Fivetran, Databricks, Imply, Versa, DBT, Yao, and Cloud Shuttle. And it goes without saying, without the hard work of Peter and a lot of these organizers, these kind of events can't happen. So I want to give a quick shout out to the team as well. So of course, Peter Hanssens, Kelly, Simon, myself, Helen, Noel, Raphael, Claudia, Aditya, and Francisco. And we also have a great committee on board, which is Nitish, Ingrid, Rohan, and Jess. So got quite a big team. It's very exciting. We're really looking forward to doing an in-person event as well. But it goes without saying, if you're thinking about submitting a talk, please do. And that's all from me. Thank you so much.
Awesome. Thanks, there. I might just turn that one off for now. Thanks, man. Cool. Awesome. First meetup for the year back in person. I just sort of thought I'd do a quick talk on Hanssens, because it's usually a little bit difficult to sort of find speakers. When you sort of first cab off the rank and stuff like that. So I'm going to take you through Hanssens today, deploying it with Amazon Neptune, which is their flavor of graph database, and the CDK. I'll take you through, if you've never heard of Hanssens, I'll take you through sort of what the deal is with that in a second. So what is Hanssens? It is an open source data discovery and metadata engine. So usually there's, I guess, two kind of consumers of this tool, analysts and data scientists. They really just want to know, I guess, what data is available, around the traps, and then obviously data engineers and software engineers. And, I don't want to sort of, pigeonhole sort of data engineers and stuff like that. But I guess, like a lot of us folks, we don't want to be explaining the same sort of concepts to people around the business all day long. We kind of just want to be sort of building out sort of pipelines and stuff like that, and then being able to sort of share our context once, which is, about the data that we've made available. And then, analysts can just go to this tool and have a look at it and go, oh, wow, this amazing piece of data in our lake or warehouse. Let's go use that. So, I mean, we've heard a little bit about data mesh and the like since, Zhamak Degani joined us last year for DataEng Bytes and took us through it. And I guess the concept is coming from domain-driven design and, microservices architecture, where you're sort of starting to look at, I guess, shift the responsibility for, making, OLAP style data available back to the sort of microservices team, rather than having this sort of centralized data engineering team that's kind of just got responsibility for the entire business. Quickly, we find that data engineering teams quickly become the bottleneck, and so so now you've got like these distributed data silos in a similar vein to microservices, and so effectively what you're looking at is you need to allow that data to become discoverable, addressable, and then all of the sort of regular old sort of considerations around trustworthiness. Working in data for as long as I have, if I had $1 for every time I asked whether this data was trustworthy, I'd probably be retired by now. But and self-describing and stuff like that. And really, where a Munson sort of comes into play is it addresses the discoverability and self-describing aspects, and a little bit the trustworthiness, because a lot of the tables and stuff like that you're storing in a Munson, the metadata of them, who owns that table. It allows you to sort of query that information so that it's a little bit easier to sort of interact and understand who owns what and things like that. So I resisted the urge or the temptation to throw in a Simon Wardley diagram, but who, if you haven't heard of him, he's like Wardley maps how sort of I guess things different technologies develop and slowly become commoditized and things like that. But really what we're seeing now is extract and load part of ETL is now commoditized. I think it's fair enough to say that in the sense that it's a little bit like your electricity bill. The more you want to pay, the more you can use. Tools like products like Fivetran, Amazon AppFlow, Stitch, they're all just kind of have particular sort of payment models where you can rapidly onboard so much data from a wide variety of sources, whether it be a SQL Server, Postgres, database, or things like Salesforce and the like. So I'm sure many of you are using these tools quite a lot at the moment. There's still a few edge cases, if you're really looking at super low latency and stuff like that. There's a few caveats around all of these tools, but generally speaking, what a lot of data teams are experiencing is this massive avalanche of data into their data warehouses and data lakes and stuff like that. And so metadata tools, whether you're in the enterprise or not, are becoming very important. And so this question comes for a variety of people is, where does this data come from? So you've got this visualization over here. You've got some, SaaS apps or something like that, or some source systems. You've ETL'd them into a data warehouse and then sort of presented them up into the visualization. And you end data analysts or business users are asking, can I trust this data in this dashboard? How do I know how it got there, or the hops and stuff like that, the data lineage? And so these are quite some common questions, and in comes kind of a Munson to solve this problem. So just to change tracks, I'll just kind of briefly talk about how what the architecture of a Munson is. It's a bit of a classic 3-tier app. So, you've just got, load balancer in your public subnet, and in your private subnet, you've got 3 containers. I'm a serverless guy, so I use Fargate to host the containers. If you wanted to deploy it the easiest way, there's a Docker Compose file, so just get a big enough EC2 instance and you can deploy it there, or deploy it locally on your laptop or something like that. But effectively, you've got 3 containers, a front-end service, which is just a simple React app, a metadata service that talks to Amazon Neptune, and a service which talks to Amazon Elasticsearch. And, You can, put Route 53 in front of the load balancer to amazon.yourcompanyname.com.au or something like that. Cool. So that's, I guess, the Amundsen architecture. You might be wondering at this point, what is a graph database? Well, you can think of it as, just storing relationships between various nodes, like, the Eiffel Tower is located in Paris, which is a city. Bill and Alice both visited the Eiffel Tower. Bob is a friend of Alice, and they're all persons and stuff like that. And so Neptune uses there's two APIs, but some of the language around this is these are edges and these are nodes. Amundsen uses one of the APIs it uses is Gremlin API, and the nodes are called vertices. So diving into what is Amazon Neptune, basically you've probably heard of Neo4j or another graph database like that. It uses Cypher as its querying language. Amazon Neptune, slightly different. It supports Open Graph APIs for both Gremlin and SparkQL. It's a fully managed graph database, so it uses the RDS control plane with horizontal and vertical scaling, as well as backups and all of that sort of jazz. So it takes a lot of the, I guess, heavy lifting away from you. Obviously, Neo4j has got like a enterprise service and stuff like that, so you could definitely use that as well. I guess the other selling point is that it's, highly secure with IAM integration, AWS VPC, that sort of jazz. So it comes with a lot of positives. The way that I've chosen to deploy Amundsen is using AWS CDK, because you can generally use it from the comfort of a programming language that you're familiar with. Who's lost a day through YAML indentation errors? No one? Maybe a few. I certainly have. So, I guess that kind of solves that. Personally, I've just gone with TypeScript to, create this repo, because it's the language that the CDK was built in. You could use Python or Java or something else like that. It's got IntelliSense and intelligent code completion and hover info. Basically what that means is, like, you can almost become like that 10x developer when you're developing your, infrastructure and stuff like that. Some of us are, really just kind of data engineering focused and maybe not so much on the DevOps side. But I've had a lot of fun working with the CDK deploying infrastructure. Progen is an interesting one. Again, who's lost a couple of days trying to set up a new repo and handle all of these sort of various package integrations and stuff like that, where you're sort of copying and pasting from Stack Overflow and stuff. Effectively, what Progen does is it synthesizes a project for you. So rather than, I guess, having a template, which as soon as you produce it, it's kind of out of date, you can always just re-synthesize it by, just typing npx progen. It'll re-synthesize your project and get all of the latest configurations for you. So if you're working with CDK, I highly recommend you check out Progen. Okay, we're done. Not quite. I had to throw in a ridiculous meme because I'm using Canvas slides and couldn't resist the temptation. But anyway, so basically, when you sort of deploy Amundsen, you've just got the Amundsen app, which is pretty cool, but then you need to actually run these data loaders to go out to all of your sort of data warehouses, databases and stuff like that, and rip out some data from the information schema. Most databases, have got an information schema that stores information like the database schema, table name, column names, the data type of those columns and things like that. And so automatically you can just grab all of that metadata and throw it into Amundsen. And here's some of the databases, metadata stores like Hive and visualization tools that it supports. It supports more than this, so do check that out if you don't see what your current infrastructure is in this slide. So the data builders, it's just basically doing ETL. It's running extract, transform, load. So it's sort of transforming into an acceptable format to load into Neptune and Elasticsearch, and then it just goes ahead and publishes it, and it becomes available in Hanssens. And so usually when you're running these data builders, you'll use Airflow. I'm a serverless chap, so I run everything with Fargate instead and trigger it with CloudWatch alarms, or I use my CI/CD pipelines to do data loader jobs. So, but you'll probably find you'll have an easier time just using Airflow, to be fair. But I've got this disease or something which requires me to do everything in a serverless manner. So yeah, and for this particular instance, like you can have different configurations where you've got Postgres or Snowflake, Tableau. You're extracting the metadata and loading it into the Neptune bulk loader bucket. And effectively, what the bulk loader bucket is, it's just Amazon doing some magic behind the scenes just to overcome some certain API limits and just rapidly onboard massive amounts of data. I would imagine in your metadata stores from your warehouses, you probably don't have crazy amounts of data in there, but I guess if you can do things fast, it's not the worst thing. Everyone can hear me well enough yet? I guess just thought I'd check. Cool. So here's kind of the full stack of Hanssens. So, that's your application, and that's, I guess, your data loader jobs. If you're interested in loading up some data into Hanssens, and yeah, obviously it all goes, sorry about the TV, goes into Neptune and Elasticsearch. Cool, so it's demo time. I recorded a demo because, I'm a scaredy cat. So this, it's a bit small, isn't it? So this is the Progen file at the base of the directory, and it's just got a whole bunch of configuration. Basically, if you go to my GitHub repo, Pete Hanssens /Hanssens CDK template, you'll be able to see all of this. In the package.json, it's just got a couple of, deploy functions, if you will. And then in the source file, you probably can't see that this is just basically how we're sort of programmatically specifying all of the various infrastructure that we want to deploy, like the VPC subnets, Elasticsearch domain, Neptune cluster, and Fargate tasks and things like that. So apologies, I recorded this afternoon, and I immediately realized that it was a little bit too small. So here we've got a couple of the Hanssens stacks in my AWS account, and let me just see, 1 second. No, we'll just keep going. Here's the VPC stack. I'm just going to try and enlarge that a little bit. And then here's our Neptune instance deployed. And then we've got our Elasticsearch cluster. One thing about Hanssens is it needs version 6.7 at the very latest. So keep note of that, but I'll include those notes in the repo. Here's the Fargate cluster with the various, with the 3 different containers, the metadata service, search service, and front end. And then just looking at some logs here, and it has just a bunch of health checks and stuff like that, just to see if it's still alive. And then we've got our CloudWatch alarm that triggers the data loader task. the data loader actually is running on the same Fargate cluster. Just out, if you're wondering, it's just easier, I guess, with your security groups and all of that sort of jazz. And yeah, so effectively, it's what this job is doing is it's just going into a Postgres database, grabbing. We've got a chatbot data set here, and it's just ripping that out and just posting it against, to Neptune and Elasticsearch. Cool. So what I'm doing now is I'm going into EC2, into the load balancers, and then getting the DNS of the load balancer, and then opening up a Munson. And this is the front end of a Munson. It's a bit of a state of affairs, doesn't have a lot of data in it because it's just a little demo. But yeah, so here's our Postgres data from, the chatbot data from Postgres, and I'm updating a description in this metadata store to say chatbot post authors. This table refers to the authors of the posts. Just a little bit of a description, so end users can actually update the metadata that you're storing. And you can also specify an owner of this particular, table. I've put my email address, peter@cloudshuttle.com.au. But I think best practice if you're doing this in an organization is to specify a team as the owner of particular tables or schemas and stuff like that, because just nicer to, I guess, share the load and be able to take holidays and stuff like that. Cool. Currently, I'm doing a bit of work at NIB, so there's a bunch of roles there. There's so many good data engineering and machine learning roles going on around. I wouldn't, but if you're interested in anything that I've spoken to tonight, I guess a lot of the stuff's happening at NIB, not a bad place. It's pretty cool fun, to be fair. So there's that. And then, thank you. My name's Peter Hanssens. You can reach out to me on Twitter, LinkedIn. That's my little company, Cloud Shuttle, or whatever. Any questions?
So ownership in Amazon, is that because it does some kind of access rights control, or it's just kind of like know who to nag if something goes wrong? So what does ownership mean in Amazon?
Ownership, it just means that, I guess, you're specifying that a specific team, I guess, looks after these particular tables, they created them or something like that. So Munsen's not that tool. I think there are tools that sort of you can sort of make access requests to, and they'll automatically provision you access to particular data sets and things, in secure environments. Munsen's more of a metadata and sort of lineage tool, lineage capabilities coming shortly to it.
I was just curious.
Oh, yeah, no worries. Good question. Yep.
I once read about Apache Atlas. Is there any overlap between?
Yeah, so absolutely. You can actually use Atlas as a backend, as a direct replacement for either Neptune or Neo4j as the metadata API. So yeah, you can it does support. There is a bit of overlap. One might argue that Atlas is a bit of work itself, and if you're already invested in Atlas, then you may as well just put a Munson over the top of that. Good question. Was it an interesting presentation?
How does a Munson handle schema changes in the source tables? Does it automatically pick them up as a schema change?
Yeah, so what you would do is you'd probably run those data loader jobs daily, because let's face it, it's not as if you're probably changing your whole data warehouse on a daily basis or whatever, or like sub daily, but so then it'll sort of automatically update that and then link up sort of, I guess, some of the metadata changes that perhaps team members have done within the tool. So, yeah.
does Hanssens provide any functionality to show lineage between tables or?
Show lineage. Yeah, it's a really good question. That capability, like there's active PRs right now that are sort of starting to roll out the lineage capability of Munson. You know, some DBT users might be thinking, oh, you know, I already get that out of the box with DBT, and I guess Munson's probably there is a way to automatically rip out all of your metadata out of DBT and bring it into a Munson, and I think pretty soon there'll be a lineage support for that. But yeah, like currently it's still in its infancy, I guess you could say. Cool. Yeah.
What are the factors that affect performance? So if I have 100 million, a couple of 100 million source records, how do you get affected?
I haven't hit that level. You know, an important thing to note about a Munson is it's the metadata of your tables rather than the actual data of your table. So, say if I was looking at a customer table, for instance, with just a whole bunch of columns, say, address and, name and all of that sort of demographic information, that's only actually probably 20 or 30 or 50 columns. And so it may have 100 million, you might be working for a company that's lucky to have enough to have 100 million customers, but what a Munson consumes is only, 20 or 30 columns. And so it'd be pretty rare, and it'd be scary if you worked for a company that had, say, hundreds of millions of columns within tables within. But I think to talk specifically to sort of performance issues with Elasticsearch and Neptune, I think generally speaking, the business users within a company are only going to be a finite number of people, and so I think I'd imagine that you'll rarely hit a lot of performance bottlenecks. Does that kind of roughly?
I can say, we're talking like something that's like document based, so the metadata changes almost with every document, and then you've got to extract out the metadata from those documents, and that becomes effectively a column. So over periods of time it changes, and across individual locations it changes.
Yeah, potentially. I mean, I haven't looked into a particular use case like that, but yeah, I mean, it's starting to get quite meta. But say if you've got a document and you've got some metadata out of the document, and then you're just storing that metadata in, say, a Postgres, database table or something like that, and then still what a Munson would just consume is just the columns from that table rather than the actual. So potentially it may not be, again, all that much data. But yeah, it's an interesting question. Sorry? Sorry?
On the chat, there are questions on the chat.
On the chat, there are such questions.
On the chat? Oh, okay.
Somebody just joined.
On YouTube.
Remember, there are other people out there.
Yes. Apologies for that. Good pickup. I'm honestly trying to attempt way too much, like live streaming, presenting. I really should have done less things tonight. But let me see if I can pull it up.
Just one person joined on the chat, and that was the notification.
Oh, okay. Yeah. There's no questions coming through on YouTube. All good. Perfect. Okay. Sorry, I'll stop being very random and let the next. So our next set of speakers, I will have to refer to my notes. We've got a presentation on setting up Kubeflow, which is pretty amazing, from the team at Rokt. So we have Iva Liu and Daniel Kovacs. Iva Liu is a machine learning engineer, and Daniel Kovacs is a ML ops engineer. So I'm personally quite excited by this talk because it is not a walk in the park to set up Kubeflow. So
Ivan first.
you can grab this from me. Yeah.
You want it then next to you?
No worries.
Let's present it alone in the beginning.
Did you want to grab that?
Yeah.
To make it easier, grab this.
Just let you do the first part.
Yeah, that's all right. Yeah, that's all right. Cool. Hello, everyone. How's everyone going? Thanks, Peter, for the great talk. And yeah, I was just talking to my colleague that this is probably the first in-person meetup after 2 years. So I'm so excited to see you guys here. And yeah, just a quick intro about myself. I'm Ivan Liu. So I'm currently Director of Engineering at Rokt, and I'm working with Kanishka and leading a machine learning engineering team to build research and build and productionize the machine learning models that being used by the Rokt platform. And tonight we've also got Dan from ML teams as a senior engineer. Together we will be presenting the running the machine learning pipelines on Kubeflow at Rokt. So just before we jump into the Kubeflow, and a quick intro about Rokt. So as Kanishka mentioned, we are actually a marketing solution company to help e-commerce business to do smarter, faster, and better. So we are processing like over 5 billion transactions, and we have partners across 16 markets globally. There's an extensive of e-commerce partners we are working with. And what that means for to make the e-commerce smarter, basically what we've observed that for e-commerce, and they are putting a lot of money to acquire customers from Google search or from the internet and get them onto their website and select the product. But after this point, there are very few optimizations over there. So Rokt is helping those e-commerce business side to continuously optimize their customer journey, even after select steps. So from the reviewing the order, make the payment, and even to the confirmation. And we are recommending the next best actions for those customers through the whole customer journey on the e-commerce website. And what that means, how the machine learning is playing in this process is we are receiving those marketing objectives from our e-commerce partners. And our machine learning will be collecting all the data through the customer journey, including the customer demographics, their behavior, and their even the creatives they will be seeing. And we will make the recommendations and call to actions for those customers to enhance their relevant experience on the e-commerce website. This can not only add value to e-commerce partners, but also enhance the experience for their customers on the e-commerce website. And to support this whole process, our teams are currently deployed like around 20 unique proprietary machine learning pipelines at scale. And we are actually using around 100 online or offline features for our machine learning and to make the real-time decisioning. And our machine learning is learning from multi-terabytes of data on a daily basis to continuously improving the algorithm. So when it comes to manage a machine learning system at that scale and that complexity, there are always challenges coming. So to take an example of the what a normal machine learning workflow looks like, and it's actually quite a standard process across the industry. So our machine learning engineers, to build a new machine learning pipelines, they will need to ingest the data from different source systems, and they will need to perform some data analytics to understand the data first, to get some interesting insights from data to see if those data can be helpful to our machine learning model. And if there are some data quality issues, they will need like missing data or outliers in the data, they will need to do the data validation and the cleaning. And after that, doing some feature engineering to transform the data into a format that machine learning can actually use to learn. And one typical example could be the numerical encoding for categorical features in the data, in the raw data. After that, our ML engineer will be doing the model training steps from data splitting, training, tuning, and validation, and locally to get the model results from it. And if we are happy about the model, they will deploy the training pipeline into a different environment, in the production environment, to schedule the retraining for those models and by using the newly coming data on a certain period. And then the model serving part will be picking up those trained model and do the real-time online decision-making. We also have the monitoring and logging system there to monitor the online model performance. If there's any feature drifting or model degradation, performance degradation, that can go back to the retrain model or even from the start to review the feature engineering. That's the typical machine learning life cycle for the ML engineer. So what will be the challenge here? So you may see, based on the preference of different ML engineer, people usually will prefer to download their data into their local machine and doing some EDA on the local machine, or they may spin up a beefy instance like EC2 instance to do the EDL and the machine learning model training on that EC2 instance. And after that, if they are happy about the result, they will deploy the model into a different group of EC2 instance. And the different model will have different resource requirements. Some model may require 20 gigabytes memory. Some model may require 500 gigabytes memory. So how to schedule those models efficiently across different EC2 instances is actually something our machine learning engineer need to deal with initially. And for the model serving, that's a different system they need to deploy to make sure the high performance and the concurrency requirements to be met. And for the monitoring and the logging, that can be another separate system. They will need to spin up and deploy to monitor the dozens of models in real time. So you will see there are, apart from actually coding the machine learning code, there are a lot of other extra work ML engineer we need to deal with. So that actually make us to think if we can actually split the needs between machine learning and engineering, if we can make the whole process much faster and consistent for our ML engineer, so they can focus on the real value-added part of building the machine learning model and improving it. If we can make the whole pipeline more reproducible, so they don't really need to rebuild the wheel every time for each steps of the workflow. If we can orchestrate those pipelines in a more efficient way here, that also is a need from engineering side. If we can integrate with different systems through that the whole pipeline workflow, if we can have the centralized monitoring logging for all the pipelines, so we can quickly observe and debug any pipeline in production, and if we can efficiently allocate those resources between the different pipelines. So it's obviously not a full list of the needs and challenges we want to solve for our ML engineering team. So if you worked on the ML ops related projects, you might have already seen this diagram. So it's a chart released by Google in 2015. So it's mainly talking about hidden technical debt in the machine learning system. If you can see the for end-to-end ML system, only this part is actual ML code. And to make sure your ML is running successfully in production, you will need to think all those dependency and underlying system requirements from serving infrastructure, feature extraction, monitoring and logging, all those things. So in my industry are improving in terms of that, but it actually give a very great metaphor about how much more we need to think about when we develop a machine learning pipeline in production. So although we have all those needs from machine learning side and engineering side, we can bucket it into 3 key features for the ML system we want to build for our engineers. So one is the composabilities. If we can break down the whole machine learning workflows into different components, and that those components can be composed and recomposed based on the different pipelines needs. So they don't really need to rebuild everything every time. And if they are portable enough, which means the whole machine learning pipelines can be deployed in any environment, and not across 6 different systems. Those can be deployed anywhere on any cloud, not AWS, GCP, or Azure, anywhere even their own laptop. If they can use the same pipeline to be deployed in staging or production different environment. And the scalability. When we talk about scalability, it's not always like adding more servers capacities. It's more about how we can scale up and scale down. Depends on the workload, how we can have access to GPUs, RAM, storage dynamically to better utilize our infrastructure. So when we think about those 3 features, actually Kubernetes comes up into this picture. So Kubernetes as a container orchestration framework, which is used to automate the deployment management and update, scaling up, scaling down for the containerized app. It actually comes naturally with all those features. So that's why over the last recent years, a lot of teams start looking into deploying their ML engine pipelines on the Kubernetes. And however, Kubernetes is not initially designed for ML development. That's why Kubeflow is actually come to in this picture. And the Kubeflow is inspired by internal project in Google. And Google was using that framework to deploy their TensorFlow pipelines on the Kubernetes. And then they open sourced that framework. And currently, they are open source teams are working on that framework and start extend Kubeflow to not only focusing on the GCP platform or TensorFlow, but also can work with other machine learning framework and other cloud provider. So Kubeflow is designed to deploy your end-to-end machine learning workflow in a composable, portable, and scalable way. You can see the very high architect of the Kubeflow. It's deployed on the Kubernetes, and it has its own applications to support different steps of the machine learning workflow, including the metadata pipelines, UI, and the serving part. So the key components our teams are using at the moment is mainly the pipeline part and the notebook part to help our data scientists to do the EDA and pipeline building. So there are also components we are looking into, including metadata to capture the metadata for the machine learning model in terms of the hyperparameters, version of the machine learning models, and also the serving part. So to deploy the machine learning model in real time directly. Yeah, any questions so far? Okay. Cool. So after adopting the Kubeflow, what the actual machine learning pipeline now looks like. So this is a code example. So internally, our ML engineering team has developed that Kubeflow SDK. So to store all those shareable and repeatable components across the ML workflow. So different team members can leverage that SDK to do their ML workflow without building that again. And so in this code, less than 100 lines code, we first import the Kubeflow SDK, and then create the ML pipeline, then leverage the Kubeflow SDK to create all those steps, including the query from our data source, unload the training data, doing the feature transformation, split the data, train the model evaluation, and publish the model into the for the real-time serving. And what this looks like is our ML engineer can deploy that script into a Kubeflow platform directly, and they will be able to see each steps of the pipeline. And each those steps is a self-contained container on the Kubernetes. So they can simply track the status of running all those steps. And without modifying any code, if they are happy with the pipeline, they can create a PR, and through CI/CD pipeline, the pipeline will be deployed to the production directly. And all the pipeline status can be monitored in a single place on the Kubeflow platform. So after that, after the adoption of Kubeflow, you will see we don't really have those 6 different systems in our workflow. Everything will be on the Kubeflow. And that makes us, our ML engineer, to focus more on the actual machine learning pipeline development. And also, they don't really need to worry about using their personal accounts to extract the data, because all those secrets credentials will be managed by our Kubeflow cluster, which then we'll be talking about more later. And it's worth to mention that for the ML serving part, we are still not into adopting with Kubeflow. The main reason I really want to raise is, although Kubeflow is providing a really good picture of how the ML workflow looks like on a single platform, but it's still maturing, and a lot of things, we've done a lot of work to actually make it reliable and stable in production. So the serving part, as in the nature of our business, we have a really much higher reliability requirements. So that part is not actually in the current Kubeflow stack, and the teams are exploring that. So I think next I will pass to Dan to talk about infrastructure and the history, how we productionize Kubeflow at Rokt. Yeah, cool.
Thank you. Hey everybody, how you feeling? Let's talk about something exciting. Let's talk about infrastructure. As Ivan has put it in words, Kubeflow is a bundle of things. It comes, like, one part is basically just open source tools that you already know and probably use, like Jupyter. Everybody uses Jupyter, right? TensorFlow, all those things. And comes with a bunch of other code that was written to basically just glue all those things together and make it as a nice package. Deploying this, like, we had a lot of issues with productionizing it, but I think the biggest issue is its version number. Like, we deployed 1.1. It should be called 0.1. Like, you know, just set the expectation, because it's like they still, like, it's super bleeding edge. Like we were encountering GitHub issues that were just raised like 2 days before, right? Like super bleeding edge, which is the good part. You can play with the shiny stuff. Bad part is that you are taking part that nobody has done before. So with Kubeflow, it is kind of like bundled. So the expectation of the user is that you wanna just get a magical cluster and then you use it. So it comes with its own CLI tool. You just type kfctl, create, and give it a VPC, and it will just magically bring up your cluster. That's very good if you don't have a cluster on your own. But at Rokt, we kind of like run a bunch of clusters. So we had a lot of scripts that is giving us like this base cluster, right? And Kubeflow was sort of like getting in the way of deploying things because it wanted to do its own. So we had to like replace it with ours. That's one part of the thing. The other is that it comes with a bunch of low-level components like Istio. Who here knows Kubernetes by heart or has anything to do? Yeah, some of you, okay. Who here knows Istio? Yeah, it's a service mesh. So like what you need to know about Kubernetes is the premise is that, okay, you give me like, I'm Kubernetes, you give me like 100 containers, you define how much RAM you want to have with each, and I just magically figure out where to run them. Service mesh is just one layer up. It's like a police in the cluster. So nobody can talk to anybody besides going through this service mesh. So it's like a security/monitoring feature. And we in Rokt, we run our own clusters and we run our own Istio. And we wanted to use those things together with Kubeflow. didn't really let us do that. So these are the steps we took to reach production. First was the very happy, it's working, like you deploy it and it kind of like does what you wanted. However, it was done with its own non-standard cluster. We have like a standard cluster in Rokt. It was done with its own one. The deployment was completely manual. So like no automation. You just run a script, like a bash script on your own and hope for the best. And no authentication, nothing. It was in September 2020. So when Kanishka came that, hey, Daniel, have you heard of Kubeflow? I was like, no. Do you want to run it in production? Sure. What could go wrong, right? Then step 2, like a couple of months later, it's automated. So like we took our standard cluster, removed some of Kubeflow's default stuff. Like it's good what it comes with, right? But if you have your own taste of Kubernetes clusters, then you want to use your own. We automated the deployment. We scripted this so-called profile creation. So in Kubeflow, you have like profiles, which are kind of like users. And it basically allows your user to access certain AWS resources. For example, if you want to have like access to the production Redshift, then you have to create an IAM role and associate it with the profile. And then we added Google SSO on top of it. So if you log in with your, like if you are logged into your Google, which we use at Rokt, then you just go to Kubeflow, Rokt.com, and ta-da, you are in. And that was good for the time being, but the cluster was tripping on itself all the time. The first interesting bit was like it can get into a cluster deadlock, which is amazing. So Kubeflow has this serving ability, so it can serve its production workloads. It has a webhook that monitors whatever is deployed to your cluster and then tries to change it so it can be served, which is fine. But it shouldn't apply to system pods. And there is like a pod kit called AWS Node if you run on AKS. And that one is like a super low-level system pod that has to work, has to come up. And this webhook was also applied on that pod. So once the service that was serving the webhook was down, your cluster couldn't scale anymore. So like things like this hit us, right? And then you wake up in the middle of the night, that production is down, and you try to figure out why is it down? And well, it was down because of that. It didn't know Kubernetes could break that way, right? But it was fun. We solved that. We had a lot of fun with MySQL. It has like 3 different MySQL databases in it. Each of them were having persistent volume issues. So if you're running on an AWS, you ask for a persistent volume, you get it in one availability zone. If your pod comes up in another node in another availability zone, it won't be able to access the persistent volume on the previous one. So your pod doesn't come up, so your whole cluster is down. We ended up basically just getting rid of all the built-in MySQLs and replacing it with RDS. So like we have the Kubeflow cluster and we have the MySQLs outside of it, so it's like safe from that sort of problem. We had a lot of fun with Istio. If you ever run Kubeflow, start with raising Istio resources substantially, like give it like a gig of RAM or 2, because Kubeflow has this tendency to, like all your experiments will run as pods, and each of the steps that Ivan shown will be a separate pod. So if you run this at scale, you will end up with like 8,000 pods or so. And Istio will want to remember all of them. So it will need a lot of RAM to do that. So we already had that problem. And the last one, no more dead nodes. Like that sounds bad, like dead nodes. Turns out that if you put enough workload on a single cluster, like a single node, you can take so much CPU into your machine learning models that kubelet, like the part of Kubernetes that kind of like does like keeping the node alive, doesn't have enough resources to report its status. And then your workload is basically killing your nodes. It was amazing because we were trying to figure out what's happening because we were just seeing node is gone. And like everything is like going crazy and the cluster is trying to bring up the missing system components in other nodes. And where did the node go? And then we realized that it was spinning so hard, kubelet, that it was taking like 3 gigs of RAM instead of the usual 100, right? 3 gigs of RAM, and it was using like 3 CPU cores. Like it really spinned it hard. The resolution for that one was to Kubernetes has this option to have like system reserve resources and kubelet reserve resources. So basically, the kubelet will protect itself from the workload, and we set that up to like shamelessly high, so it doesn't die anymore. And it's stable since, so no dramas. Like it's been running fine. And the last thing we've done was scaling. So initially, we had like a naive setup. Like we had our control plane, like the main Kubernetes, and we had the worker nodes. It was just like one size fits all. It was, I think it was a M5 4x large or something like that. Yeah. It has like a reasonable amount of CPU, reasonable amount of RAM, but not too much. And they couldn't run a couple of workloads. They have some training jobs that needs like a little bit of 300 gigs of RAM and stuff like that. It didn't work. So like setting the instance size up for the workload to like a large instance, you would generate a lot of loss because that model doesn't run all the time. So what we ended up doing is we ended up creating multiple worker node types. So we have like 4 different types of worker nodes. We have like one that is a CPU instance, like a C5 18x large. I think it doesn't give anything anybody, but it's like it has 96 CPU cores, so it has a lot. And then we have another one which has like half a terabyte of RAM. And then we have another one which is like a smaller version of these things. And we set up the cluster in a way that based on what you deploy, it will figure out what's the best size of node to bring up to suit your workload. And these worker nodes are prioritized based on cost. So it will try to serve your need with the cheapest option. If it can't be fit on that because it needs more RAM or more CPU, then it will fall back to more and more expensive options. And that's May 2021. So this is where we are at. And this is how our cluster works now. So each color is a different type of node. And you can see this is the last week. And you can say that the cluster, like you can see that the cluster is scaling up and down quite aggressively. So it spins up a lot of different types of nodes based on what it needs, and then it spins them down. So in the daytime, like people are usually training their model and testing stuff, so there are more nodes. When it's nighttime and only the scheduled jobs are running, then it like scales down and becomes like flat. This is a huge cost saver. And what we managed to do with this is we reached like roughly 50 to 70% resource utilization. So if we take a machine, we use at least half of that resource that we pay for. So these are the graphs that the square one. That's the allocatable, like this is how much you have. It scales up and down. And the curvy one is how much you actually use out of that. So like you can see that it's like following quite nicely. So that's where we are at. I don't have a last slide, but the last slide, where do you want to go from here? We need to upgrade the cluster. Kubeflow 1.1 is the version we're using. We need to be on 1.3. And we want to introduce GPU nodes slowly, as Ivan and his team is moving towards.
Deep learning.
Yeah?
Deep learning. Sorry.
Yeah. They move towards using neural networks. And we probably want to achieve even better reliability so production load can run on the cluster. That's all we got. Yeah, questions?
I have lots of questions, but I'll just start
Okay.
with one. For smart scaling, say if there isn't enough memory to do a job, does it always have to fail first before being promoted to the higher cost alternative, or does it have some kind of learning and it knows that these jobs just put them on the more expensive one straight away?
Good question. So Kubernetes runs with scheduling pods. So when you create a pod, you are basically saying that I want this to run somewhere. And then the pod initially becomes just pending, which means that the cluster is trying to figure out where to put it. If it's too big, then it can be scheduled. So it's not like a failure, it's just waiting to be scheduled. There is a component called the cluster autoscaler that will notice the situation that there is something that cannot be scheduled, and then it will figure out which node type to scale. and it does the scaling. It takes like half a minute, so 30 seconds for a new node to come up. New node comes up, registers itself, and then the pod becomes scheduled.
Last question for now. Will these slides be available?
What's that?
Will these slides be available?
It's up to Kanishka.
Yeah, we can make them available if you're happy.
Yeah. No company secrets in this. No access codes. Nothing. No future plans. No. Okay. Yeah. Anybody else has a question?
I've just got one question.
Yep.
So you're going through all this data, you're sort of just loading data in, and you transform the data, you sort of feature engineering workflow. Are you doing any horizontal scaling at any of those stages, or do you just scale up with the sort of bigger pods, basically, or stuff?
There is an aspect of horizontal scaling. I think small budget and those things like running with like thousands of pods.
Yeah, so
I think it's a question for Ivan.
Yeah, for the feature engineering part, we are not doing any horizontal scaling.
More closer to the mic.
Yeah, sorry. Yeah, for the feature transformation and feature engineering part, we are not doing horizontal scaling at the moment. But for the model training, we're actually doing the horizontal scaling to train model by, for example, by different partners, by IDs, but they will be using the same training data.
Okay, so but it's by partner interface, so each partner is actually doing its own training, its own unique ways.
Yeah.
So it's not like you do the same training across multiple nodes, you get the same weights in the output.
Not distributed training, if you are talking. Yeah.
Okay.
Yeah. Cool. Awesome. Yes, please.
Some would say that Kubeflow is quite opinionated in how it does things. Did you guys ever look into Argo? Do you know of any areas where Argo would be massively worse or massively better than Kubeflow for your use case?
So Kubeflow itself is using Argo, I believe.
Yeah.
So what's your question?
Well, I guess, yeah. Is there some areas where Argo may have been better than Kubeflow or versus?
So in the 1.1, Kubeflow is actually using Argo for the auto scheduling and the pipelines. And I know in 1.3, it's also start using Tecton for the pipeline scheduling, pipeline scheduling. Yeah. So theoretically, it should be similar to Argo.
The Argo, the pipelines are, the Kubeflow pipeline is built in Argo. The Argo is more like a lot more generic, but Kubeflow's kind of fit our specific use case because we just wanted to build ML pipelines.
Yeah, Argo is more like Kubernetes Airflow.
As far as I know, it's a lot more generic. You can use it for any other use cases. We have very specific use case of building ML pipelines. That's why we're down the Kubeflow.
I have a more like kind of generic question. So I don't know, it's obviously been a long year. You've done a lot. Seems like there was kind of a lot of pain and engineering work along the way. Like with 2020 hindsight vision, would you make the same choice, like of technologies and around?
I wouldn't. They are the users, so they have to know.
What was it worth it? That's what I'm trying to ask.
Yeah. So I haven't joined Rokt in 2020, but I think there are not many choices in the market back to 2020, and Kubeflow probably was the one of the very few open source tool. The reason we are making that decision is also about we don't want to really bound into a particular cloud provider. Although the multi-cloud strategy is not that sound, but it's actually gradually become more and more important over time to the companies who are running their business on the cloud. So that's also one of the main reasons we are choosing Kubeflow.
Yeah, the options we had were like, because I haven't joined a bit later, I was like involved earlier in the early stages. We had MLflow, obviously SageMaker. We looked at SageMaker, and SageMaker didn't have all the features that we wanted. Their serving wasn't that great, and all of the hosted AWS hosted servers, those kind of things are pretty good. Like if you have small traffic, the scale that we're at, it just becomes super expensive because it just doesn't make sense. because at some point it's like it's easy to start, and we did that in the early days as well. And as you're getting more scale, then the cost just becomes so high that you start to learn. It makes sense for you to set up like Kubernetes in one class or something like that. So there was not ML flow, and then I think there's from every ML flow is one, but doesn't have all the features. There's the kubeflow has. kubeflow has all the features, but it's still in the early days. So yeah, there's not many other things in the market. It's and not many people hit these kind of problems as well. Like you only hit these kind of problems when like when you need a feature store, like you need like consistent pipeline. I'm building things that's at a certain scale. If you're building very simplistic pipelines, you're fine just putting it on a notebook or whatever, running a cron on your computer or on EC2, that's fine. And we would do that in 30 days. But the requirements for us are so rigorous that we need to go away from this. It's a new thing for everyone now, I think. Like feature stores and kind of kubeflow. Yeah, those type of things are
cool. Thank you. Right. I just want to quickly add, as you can see at Rokt, we are conquering the frontier, and we have, apart from the MLOps, we have other many exciting projects. So I put this little link here. If you are really interested in a role at Rokt, we have many opening roles here.